Hello everyone, welcome back to my class, and now we are in module 6, and in the last class of module 6 we discussed about multiple beam interference, and there we talked about multiple reflections and multiple transmissions, and we saw that multiple refractions generate fringe pattern, and similarly multiple transmissions also generate fringe pattern, and we also learned that how an incoherent extended source generate a sustained interference fringe. Today we will start Fabry-Perot interferometer and Etalon. Now, the multiple beam interferometer first constructed by Charles Fabry and Alfred Perot in 1800. Yeah, this is the Fabry-Perot interferometer is again interferometer which relies on multiple beam interference, which we discussed in the last class, and this type of interferometer was first constructed by Charles Fabry and Alfred Perot in 1800s, and is of considerable contemporary interest. It has a very wide scope in spectroscopy, in microscopy, and we will see here. Now, besides being spectroscopic device of extremely high resolving power, it serves as a basic laser resonant cavity. Yeah. Now, in today's or tomorrow's class, we will learn that how to calculate the resolving power of Fabry-Perot interferometer. But how does a Fabry-Perot interferometer works as a laser resonant cavity? This we will learn while talking about lasers. Now, the third point in the introduction of Fabry-Perot interferometer is that the device consists of two parallel planes. Yeah, the device as we saw that in thin film interferometer, there were one film which is of course bounded by its interfaces. Here Fabry-Perot interferometer, it consists of two planes and which are made highly reflecting, and these planes are separated by a certain distance d. Yeah. Now, if the gap d can be mechanically varied by moving one of the mirrors, like suppose we have two mirrors which are separated by certain distance d, and if I fix some micrometer on the back of one of the surface, and then the d can be varied, and if we are able to vary the separation between the two mirrors, then it is referred to as interferometer. While when the mirrors are held fixed, when these two surfaces, if we fix it, okay, and adjust it for parallelism by screwing down on some sort of a spacer, suppose we fill the distance the space between the two mirrors or two surfaces with some fillers or some spacer, and therefore we would not be able to now change the separation between the two mirrors. Yeah, the d is fixed now. In this case, this interferometer is called Etalon. Okay, but you can see here that you can use interferometer, Etalon almost synonymously. Okay, the only difference is that when d is fixed and parallelism is removed, it is Etalon. Okay. Now, this is the typical schematic diagram of Fabry-Perot Etalon. Okay. Here you see that we have a glass slide, and this is again a second glass slide, and on the inner surface of this glass slide there is a coating, and most of the cases this is a metallic coating. Okay. And what does this metallic coating do? This metallic coating has very high reflection coefficients. Okay. And that therefore it efficiently reflects the light. Okay, where does the light come from? The light comes from a very wide source, which is very broad source, and the broad source is represented here with this shaded rectangle. And now you can see is that this is a broad source, therefore here again we have multiple number of point sources. Okay. Now, say there are 2 point sources which are S1 and S2 here. The ray from S1 is start, and then it falls on the Fabry-Perot interferometer, and then it suffers multiple reflections and transmissions. Yeah, these are the reflections, and then within the film rays internally reflected, and then here we are getting the transmitted light. Okay, and this transmitted light is now collected through a lens, and it falls on the screen where it overlaps and generates some interference pattern. Okay. Now, all the rays either in reflected arm or in transmitted arm, if all these rays are emanating from source S1, because so there is a particular ray which is falling on the this interferometer, and then multiple reflection and refractions happen. Yeah, multiple reflection and transmissions happen, and out of this multiple reflection and transmission, out of the same source S1, multiple reflected and transmitted rays are generated, and these rays are perfectly coherent with among each other, with each other. Why? Because they are getting generated from the same source. Yeah. Similarly, suppose there is another point source S2, which again emit a ray which falls on this spectrometer, then the reflected and transmitted rays which owes its origin in S2, they would be mutually coherent, but the rays which are having its origin in S1 would be incoherent with the rays which have their origin in source S2, because source S1 and S2 are incoherent, they are not correlated. Okay. Therefore, the pattern which we see on the screen, this pattern, this would be the concentric ring type which we have already studied for thin film, and the each circle, be it a dark circle or a bright one, each circle represent a set of rays which falls on the same angle on the interferometer. Okay. And therefore, these fringes are fringes of equal inclination. The coherent rays which are parallel, they will fall on the same angle, and they will fall on a certain point of a same circle. Okay. And these circles are made by the rays which are parallel. Okay. The points, the different points on this circle are made by rays which comes from some point source on the broad source. Okay, but not necessarily from the same point source, say S1. Okay. This point may have its origin in S1, this point on this circle may have its origin in S2. Similarly, this point on this circle may have its origin in S3, but still they are forming or they are falling on the same circle. Okay. They may have their origin on different point sources which are completely incoherent, but they will fall on the same circle because they are parallel, they are falling on at the same angle on the interferometer. Okay. And this is what we detailed in our last class, that why a incoherent source is giving a sustained interference fringe pattern, and this is what exactly is happening in Fabry-Perot interferometer too. Okay. Now, you see that these glass plates, they are slightly wedge. Okay. They are not perfectly parallel. Here they are thinner and here they are thicker. Here they are thicker and here they are thinner. Okay. On this side you see the glass plates are thin, while on this side they are thicker. The inner surfaces of these glass plates are although parallel, but outer surfaces, these surfaces are not parallel, they are slightly wedge like this. Okay. They are this wedge shape is deliberately introduced into the system just to avoid interference of the reflections which are happening at these surfaces. Okay. We do not want to see the reflections out of these outer surfaces on our in our field of view, therefore, we deliberately make them wedge. Now, the unsilvered sides of the plates are often made to have a slight wedge shape, as we discussed few minutes before, and this wedge is of a few minutes of arc. The angle, wedge angle is very small. Okay, and why we do this? We do this to reduce the interference pattern arising from the reflection of these sides. We do not want this extra reflections to come in our field of view. Okay. The multiple waves generated in the cavity, cavity means the space between the two inner surfaces. Okay, the multiple waves generated in the cavity arriving at point P, which is on the screen, from either S1 or S2 are coherent among themselves. Yeah, the light which is coming from S1, it would be coherent, yeah, because the multiple reflections and multiple transmissions are being generated from the same source. Okay. The rays arising from S1 are completely incoherent with respect to those from S2, yeah, and so that there is no sustained mutual interference. The contribution to the irradiance IT at P is just the sum of two irradiance contribution, yeah, and this is what we talked about here. But this distribution would be completely incoherent with this distribution, but they are independently sustained, therefore, overall pattern will look sustained. Okay, all the rays incident on the gap at a given angle will result in a single circular fringe, this we know, and this would be of uniform irradiance, okay, because the source is very broad and the rays will fall from different angles and finite many rays are there, then roughly the irradiance of the circle would be same and it would be uniform, yeah, and at large value of d the rings will be close together. Yeah, if you increase the separation between the interfaces, the air gap will increase or the cavity width will increase, and this will ultimately reduce the radius of the fringes, and fringes will shrink. Now, this is again the schematic of Fabry-Perot Etalon. This is 3D schematic. You see here a source which is wide, very broad, and then this is the lens which is falling, which is directing the light towards the Etalon, and here Etalon multiple reflections and transmissions are happening. All the transmitted rays are collected through this lens and they fall on certain point on the screen. Yeah, and if you collect all the pattern from all the points on the source, then you will see that it is forming a concentric ring pattern as shown here in this figure on the screen. Now, to increase the reflection, as I said before, people usually use metals, but we all know metals are lossy. Therefore, apart from coefficient of reflection and coefficient of transmission, we will also have to take into account coefficient of absorption, yeah, because there is losses which are there due to the involvement of metal. Okay. Therefore, partially transparent metal film, although the metal is very thin, it still would have losses. Okay, but since the metal is thin, therefore, we can say that it is a transparent metal film, partially transparent metal film. So, then the statement says that the partially transparent metal films that are often used to increase the reflectance, okay, small r is the amplitude reflection coefficient and capital R is intensity reflection coefficient or irradiance reflection coefficient, and they are related through this relation, capital R is equal to small r square. Okay. And therefore, the metal will absorb a fraction A of the flux density, okay, some part of the intensity will be absorbed into the metal, and this fraction is referred to as absorbance. Okay. Therefore, initially we were into the habit of seeing this relation T t prime plus r square is equal to 1. Okay, this is the amplitude reflection coefficient. You can write the same equation in terms of intensity reflection coefficient or transmission coefficient. Okay, this capital T is the transmittance or intensity transmittance coefficient, and this is your intensity reflection coefficient, which is of course in capital, and capital T is related to T t prime. Yeah, capital T is equal to T t prime and capital R is r square. Therefore, the same relation can be expressed in this form, capital T plus capital R is equal to 1. But since we are using metal, absorbance also comes into the picture, and therefore, this equation 26 modifies to equation 27, which is T plus R plus A is equal to 1, okay, and this shows the conservation. Okay. The total transmittance plus total reflectance plus total absorptance, they must be equal to unity. Okay. Now, since we are using metallic film, it will introduce some additional phase shift, say phi, okay, and this phase shift can differ from either 0 or pi. Okay. We are into the habit of considering additional phase shift of 0 or pi due to the internal and external reflection, but due to the incorporation of metal, we can have either 0 or pi or some other phase. Okay. The phase difference between the two successive transmitted wave, therefore, in the case where metal is involved is equal to del, which is given by 4 pi nf by lambda naught d cos theta t plus 2 phi. This first part we are familiar with, it is k multiplied by 2 nf d cos theta t. Okay. Nf is the refractive index of the material which is between the two edges of the Fabry-Perot interferometer, whose thickness is d. Yeah, Nf is the refractive index, cos theta t is the angle of transmittance, we already know about it, and phi is there, it is a twice of phi because the ray is falling and it is passing twice into the metal film. There are two metal films on each side of the internal interfaces, therefore, it is passing through the same thickness of the metal twice in one round trip, therefore, 2 phi is there in the phase term. Okay. But in general, the metal film thickness is very small, d is very large and lambda is very small. Lambda, you just notice it is coming in the denominator, lambda is small and d is large. Therefore, this first term in equation number 28 on RHS is very large as compared to the second term, which is 2 phi. Okay. And therefore, phase term, this phi term can be neglected from equation number 28. Okay. And therefore, from this thin film relation, and we studied it in our last class, the equation number 17 modifies to equation number 29. Yeah, the relative transmittance irradiance modifies to equation number 29 here. Okay. Now, here in the numerator we have capital T, but we know capital T from equation number 27, capital T is equal to 1 minus R minus A. Let us substitute for that. Then if you do this substitution, then ultimately we will have this relation for the relative transmitted irradiance, and which is given by equation 31. In this relation, we have introduced again this Airy function. Yeah, that is the typical function which we studied in our last class again. Okay. Now, here in equation 31, we see that there is absorptance which is appearing here in this right hand side. Okay. If we neglect absorptance, then 31 reduces to 32, and which is the typical expression, the same expression which we studied in our last class. The I t upon I is equal to italic A theta. Okay. This is the special case. Yeah, it is a special case where we neglect absorptance. Okay. But not, this is not usual the case. Yeah, and therefore, we will continue with equation number 31. Now, the peak transmittance is given by I t max by I I, and what would be the peak transmittance? 31 maximizes, 31 peaks when A theta or italic A theta maximizes, this Airy function maximizes, and what is the maximum value of italic A? It is 1. Okay. Therefore, the maximum relative transmitted irradiance is equal to 1 minus A upon 1 minus R whole square. Okay. This is given by equation number 33. But if you want to calculate the relative irradiance, then it will still be decided by italic A theta, the Airy function. How? If you want to calculate the relative irradiance, then multiply the usual irradiance or divide the usual irradiance with equation number 33. Okay. normalize all the irradiances with IT max, and if you do this, this factor will go away from the expression and you will get A theta. Now, if we want to do, then use equation number 31 and 33. If you want to write the relative irradiance, then perform this, then from here what you get is that IT upon IT max, which is nothing but relative irradiance, relative transmitted irradiance, this would be equal to italic A theta, which is nothing but Airy function, which is written here in this statement. The relative irradiance will be determined by italic A theta, the Airy function. Okay. Now, let us look on the fringe pattern which we see in Fabry-Perot interferometer. Now, to see the fringes, we have to plot IT by IT max, which is nothing but your Airy function. Okay, if you plot this Airy function with del, the phase, the things which is very much clear from our previous classes is that maxima will appear when phase is integral multiple of 2 pi. Okay. Therefore, the phase maximizes when del is equal to 2 m pi. The next peak will appear when del is equal to 2 m plus 1 pi. Okay. This is what is written here, 2 m pi, 2 pi in bracket m plus 1, the next integer. And this is how the maxima repeats itself, and you can see that the two consecutive maxima are separated by 2 pi. Okay. And all these peaks, maxima peaks, has certain width. Okay. And the width is represented by gamma, and it is measured at value when the Airy function reduces to half, it is a half width. How to calculate the half width? Del 1 by 2 is the half width. Now, if you move from the center by del 1 by 2, then you get this edge, and if you move on the right hand side from the center by del 1 by 2, then you get this edge. The difference between these two edge will give you the width. Okay. This would be equal to twice del half. This plot is plotted for f is equal to 200 and capital R is equal to 0.87. You see that f, which is a coefficient of thinness, is very large as compared to 1. Now, you see that the fringes would be sharp if the width is smaller. Okay. And this is what is written here, a measure of the sharpness of the fringes, that is how rapidly the irradiance drops off on either side of the maximum, is given by half width gamma. Okay. If the gamma is small, the irradiance falls off quickly and the width of the peak would be smaller. If gamma is large, the irradiance falls off slowly and the gamma would be larger. Gamma is the width of the peak in radians when IT is equal to IT max by 2. When irradiance goes below by half, then only we measure gamma, and there only we define gamma. Yeah, and this is also clear from this figure. Yeah, the gamma is defined where the relative irradiance becomes half of its maximum value. Okay. Now, the peak in the transmission occur at specific values of the phase difference del, and where does this occur? Where this occurs where phase difference is integral multiple of 2 pi, that is equal to 2 pi m, where m is an integer. The del maximizes when it is equal to 2 m pi, and irradiance will drop to half of its maximum value whenever del is equal to del max plus minus del half, and this is what is shown here. Yeah, these are the edges which defines the gamma, and here the value of del is del max minus del half, and here the value of del is del max plus del half. Yeah. Now, if you calculate, if you know the phase, the value of phase difference, calculate the value of relative irradiance there, and you will see that it is half of the maxima. Now, the phase difference, the difference between these two phases will give you the width of the peak. Now, we know that on the vertical axis we are plotting this Airy function italic A theta. At half maximum A theta would be half, okay, because the maximum value of italic A theta is 1. Therefore, at half maximum the value of italic A theta would be half. Therefore, this relation would be intact, and here we can substitute 1 by 2, and from this relation we can calculate the expression for del half, okay, which is the half width, okay, and del half is 2 sin inverse 1 by square root of f. But we also know that f is generally very large, okay. When these resonances in these peaks are very sharp, then usually f is very high, okay, and if f is very large, then this term would be very small, and if this is very small, then we can substitute sin inverse 1 by square root of f with 1 by square root of f, okay, and therefore, the expression for half width would be modified, okay. The half width as is given by twice of del half, it will after this substitution would be equal to 4 by square root of f, okay. I repeat, here you see the del half, but if f is very large, then you can replace it with 1 by square root of f, and we know gamma is equal to twice del half, okay, because in this figure you see gamma is the width f at half irradiance, and what is this width? This width is this phase minus this phase, and if you subtract these two, then you will get 2 del half, which would be equal to your gamma, okay, and therefore, gamma is 2 del half we know, and therefore, gamma would be 4 by square root of f, which is given by equation number 37, okay. The half width gamma is equal to 4 by square root of f, and we know f is coefficient of thinness, which is given by 4 r by 1 minus r square, and capital R is equal to small r square, okay. Now, larger the r is, sharper will be the transmission peaks, okay. Larger the r is, sharper would be the transmission peak. Alternatively, larger the coefficient of thinness is, sharper would be the peaks, okay. Now, there is another very important parameter which we must know, and this is defined by the ratio of separation of adjacent maxima to the half width. What is the separation between the adjacent maxima? The separation between the adjacent maxima is 2 pi, and what is half width? Half width is gamma, okay. Then we define another parameter which is known as thinness, not coefficient of thinness. Coefficient of thinness is capital F, and thinness is this italic f, yeah. Notice the difference. The thinness is defined by ratio of separation of adjacent maxima to the half width, and therefore, thinness would be equal to 2 pi by gamma. If you substitute for gamma, then you get this expression where thinness would be equal to pi square root of f by 2, yeah. This is coefficient of thinness, and this is only thinness, okay. Do not get confused. This is all for today. In the next class, we will talk more about Fabry-Perot interferometer. There we will see how the resolving power is measured, what exactly is the resolving power, how it is useful for the usual optical system or spectroscope, how can it be used as a spectroscopic tool. This all would be covered in the next class. For now, it is all. Thank you for listening me.